Well, today I wanted to go through uh, this thing like simulation stuff, and then maybe a little bit of machine learning stuff. They're kind of somewhat related, I guess. And we can't, I mean, you can't go through the whole thing, but basically we can touch on some things. Then Friday, uh, Ugo Okali from Tennessee is going to do Zoom. So you should bring in your PC, your laptop if you can. If you don't have one, then team up with someone that does, or if you have a desktop, do it on Zoom at home or something. Because he'll show you like the download to download all the stuff and then install it, like get everything running, and then like go through the first five parts of it, and then the sixth part is like more challenging to do the actual thing that he wrote a Nature paper on. So you can, it's not that much more challenging, but basically probably you can't go through that one in class. And then the next week, I guess there were a few people that were doing membranes. So I guess I'm going to go through membranes next week, like polymer membranes. And then there's a Sanat Kumar. I noticed he published a paper on membranes here. Let's see, 2025, like this year, there's this membranes paper. Guess that I guess that thing's not linked right or something. I'll have to fix that. I wonder if the other things are okay. These are the two papers. This is the two papers from his talk. Like so he was talking about microplastic, like he showed this slide, for instance. So that's a Nature paper, and there's also a soft matter paper. Those two worked, but the other one didn't. That's pretty weird. That's on tire particles. He talked about that too. So Nate, he had to cut it short, so I thought I'd put those up there in case you wanted to see the full story on it. And then this thing will eventually be there. Gas permeability and polymer grafted nanoparticle membranes. So he did nanoparticles composites. This is like applying it to membranes. So it should be okay so that'll be on one of the papers on the final. And then the other paper will be something that's like a kind of a qualifier question. So it'll be like more general. Like those normally you don't exactly need to have the paper to understand it, but I'll give you the paper, but basically it'll be like some questions to answer. So anyway, the undergrads, so if you're a senior undergrad, you don't need to take the final because it's like a rule, you're not supposed to take finals as a senior undergrad. But if you're not a senior, you have to do it. So it's kind of a drawback to not being a senior. You guys are both seniors, right? Or you're grad, are you undergrad? Oh, 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 so none of the undergrads are here because they know that or something, or I don't know, whatever. I always think you two are like undergrads or something, but I don't know why. But anyway, so you guys have to do it. And so it's gonna be like two kind of homeworks, but the second one should be kind of easier. And then the first one will be this thing on the membrane stuff. And then so that's about it. So let's see. So let me do this thing. So any questions on the homework or anything? So homework's due today at midnight, but I guess I only had like two emails on it. So I guess it should have been kind of easy, well, pretty easy, I guess, but anyway, hard to tell. Um, anyway, so that's what I'll be drawing. I'll put these here, put those on. Anyway, so this is actually from I teach a thermo class, advanced thermo. So this is kind of from that, notes from that. So it's a little bit materials based, like metals, ceramics, polymers. I think it's good because you'll see this. Um, you'll see like DFT mentioned a lot. Even in one of the Polymer papers we had, they chose, I forget which one, but they used DFT to feed into a molecular dynamics. So that's a lot of times how you'll see it. If you're doing just ceramics or metals, then DFT is like the whole thing you do, and you want to know like the electronic states of the material. Like if you wanted to know a semiconductor's properties and you wanted to dope it differently or something, then you'd use DFT to do that. So so that's like the base states. You have like quantum mechanics gives exact calculations for the wave functions for electrons, but you can only do simple things with it. So if you get to real materials, you have to cheat. So you have to kind of simplify everything, and that's what density functional theory does. So it allows you to do electron, so subatomic particle calculations to build up a structure like a crystal on systems that are too complicated to do with quantum mechanics. So it's complicated. The density is density of electrons, electron kind of cloud, so anyway, so that's the base state. Like if you wanted to do that, but if you want to do that for a polymer, it would be too complicated. And also this isn't open source software. This is all proprietary software. So it's all black box. So you have to kind of believe that it's true. And also it's going to cost like 200 grand to buy that software, and it's not available. You can't just download it from China or something, or Russia, so basically you're stuck with the 200 grand. So you have to find someone that's already got it and use it, or get a grant that's going to support doing that kind of thing. And it's kind of a catch-22, because if you don't have the software, you can't exactly learn how to do it. So you can't really write a proposal for it. So you have to be in the club already to use this thing, right? It's like a members only kind of thing. And then you can do this kind of odd thing that's useful. Like if you're in microelectronics or something, it's useful. And then also if you want to know, so in the Polymer paper, I forget which one it was, but they used DFT to get the base state. And what they did was they collaborated with someone who had already paid the 200 grand and then also knew how to run it. So they just took the output of this and fed it into a molecular dynamics simulation. Right. So anyway, and also you can do ab initio molecular dynamics is actually going to deal with atoms and molecules. And generally we're dealing with spheres. Like in polymers, you just say it's a sphere and you have a 612 potential interaction, and it can have charge. So you have coulombic potential interactions. And then you have springs and various kinds of springs to deal with the chain, the bonded parts of it. Quantum Monte Carlo, I guess, is like Monte Carlo, but on quantum. I don't know anything about that. So basically, this is more or less like if you're doing material science and you're on the physics end of material science, this is the only thing you would use. Like if you, especially ceramic materials, electronic materials, and some metals. Like there's a paper like what's it called? Entropy metals or something. High entropy alloys, which is like you mix so the mixing is driven by entropy rather than enthalpic interactions. So it's kind of like mix a bunch of things together so they have high entropy. Anyway, so that's going to use DFT to model. Like so those are kind of areas where we would do that. Metallurgy and ceramics. And then input into some molecular dynamics for polymers. Then within the polymers, so you're going to have basically break down the structure, so coarse grain it to some degree or to a large degree. So you can, coarse graining can be like, it's very similar to an atom, or it's a collection of atoms, and it's got potentials that are kind of realistic that you can link to experiment, or it's so coarse grain and you don't even use like 612 potentials and things. You just make up some potentials that are very simple, like linear potentials that can be computed faster. Right, so that's like DPD simulations. So like in the lamps thing that you're going to use on Friday, you can do, it's written from like the dynamics. You can use it for DPD just by swapping out the potentials. So you just say use this potential, and it can do a DPD simulation, and it can also do Monte Carlo simulations. So it can do that one package can do the three things: MD, Monte Carlo, and also DPD, right? And then these others are for metals and ceramics. Anyway, the idea is still true that you want to predict some kind of property and have some kind of model that you're starting with, and then predict the property. Anyway, so that's a picture. So these are kind of like pictures of how people look at simulations, right? Like this is another one. Like you can talk about the size scale that you're looking at. Like if you do macroscopic, then you do something I never do, but recept the material as a lattice, and then you just have spring constants between everything. What's that called? It's a continuum mechanics approach. So you can do simulations of like a bridge or some large scale structure. Or if you're injection molding a part, then you use this kind of simulation, right? So you can simulate large scale things, and then you can simulate the atoms and molecules with density functional theory. And somewhere in between, you get to this mesoscale thing, which is where some people are really interested, right? So this is where, so this in between scale between atomic and bulk. I can never remember the name of that simulation. The mechanical engineers use it all the time, right? To simulate a large scale structure. No one knows it. And it's not written here. Should have written that here. Anyway, so this is just showing like the size scale they're interested in, because if you try to do a DFT to model something like a liquid crystal phase separation or structure formation, you would use up too much computational time. It's too expensive. So you need to simplify the system, then but still have like interaction potentials that match up well enough so that you can predict what happens. Then you basically try it and see if it matches with experiment. If it does, you say it worked. So there's no direct point where you say I can cheat and say that things are spheres. It's just a matter of like you do it, and if it looks right, it's right. So at some point it isn't really science, but at some point it's just like it looks right, so it must be right. Which maybe in a sense that's what science is, but basically it tends to be in terms of argument based on some facts. So the simulation thing is actually not based on facts, especially the coarser grain you get, the less facts you have. Once you get to the continuum mechanics, it's just I kick the dog, it barked. So and then I kick it twice, it barks twice. So I have a constituent parameter that says they're proportional to each other by a factor of 1. So my modulus is like 1 for kicking dogs. That's no thinking at all. It's just like kick the dog, count, Or if you get bitten, then you went over the linear dependence part. You've gotten to where it breaks down. Right. And if you didn't kick hard enough, the dog wags its tail. So there's 2 limits to that linear regime. Right. So anyway, that's the continuum systems. Here you pretend that you know what you're doing, but you actually don't. And here you know what you're doing, but you can't really predict anything. So you kind of have these limits of where you can operate. I mean, this is where the interesting things happen, really. This is like building a bridge. So it's like you kind of know, I mean, you more or less know the answer, right? And then here, you don't know the answer, and it comes out with answers. Here, it's only good if you're looking at very small scale, like the DFT stuff's only good if you're interested in just one molecule and how it acts. So this is another picture also taken from this talk. This is like Brown University. I forget who it is, but I guess it's not these people either. But basically, they say like micro, meso, and macro. So you see those words tossed around, and so micro sounds like micron, but it isn't. That's a little confusing. And meso is colloidal. Like colloidal is a better word to say than meso. But these words come from gas absorption measurements when you look at porosity. So you stick a thing in and nitrogen will absorb to the surface or adsorb to the surface. And then you weigh it and see how much absorbed, and then you get the surface to volume ratio, and 1 over that's the Sauter mean diameter, the size of the pores, right? So basically, with that analysis of gas absorption, the people that did that which is like the BET guys, Emmett and Teller and B. I don't remember what B is, but they and Langmuir even before after Langmuir before anyway. So they came up with those words that talk about macroporosity, which would be like a sponge on your sink, and then mesoporosity would be something like an aerogel, and then microporosity would be a zeolite, like in other words, molecular scale porosity. So they use those words to say to describe porosity, and then they've borrowed those words in a couple fields, and it was like simulation, right? So you can say simulations are micro, meso, macro. You're undergrad, right? Yeah. Oh, all right. See, I thought you guys were all undergrads. Undergrads don't have to take the final, but masters do. So anyway, so so if you look at it in terms of those words from gas absorption, you can say like molecular dynamics is kind of looking at micro. I guess the DFT isn't in this scale. So these are only things that are interesting to look at for me, you know. So micro, meso, macro. It is pretty, to me, really confusing to call something micro when you're talking about atomic level. Like micro should be a microscope at a micron scale. No, but anyway, they use it this way. And meso means this in between like colloidal, like soap vesicles or something like that. Our biology is kind of on a meso scale. So anyway, so that's kind of another picture of it, right? So it's showing like, start with these things in coarse grains. You say that collection of those molecules that are floating around becomes a sphere, and then the spheres interact with each other, and you can build up structures that way, right? In fact, it doesn't exactly work that way, right? In other words, you can, if you change the conditions here, it can affect the small things, and that macroscopic can affect this stuff, and this assumes this is going to be all right. So if you're a metallurgist, a ceramicist, you assume that like you have two atoms. It's like they predict the modulus for a ceramic or a metal based on the covalent bond strength. So your bulk modulus, which is beyond macro, it's like the building, you know, is based on an atomic scale prediction. And there's nothing in between those that would change that, right? So that's true for some metals and for some ceramics, but for everything else, like the human body, that's definitely not true. So most of the things, a tree, that's not true. Like, is a tree going to blow over in the wind? The atomic bond strength of the carbons in the tree have nothing to do with it, essentially. Like bamboo and a tree have the same carbon bonds in them, same bond strength. Bamboo will just bend over and flop back up. The tree gets uprooted and blown down the street, right? So basically, complex things you can't just say like, I'm going to make a sphere that's composed of those and make the other thing, right? So there's a lot of problems with like fitting this thing together that you have to kind of consider that people will overlook. So anyway, this is a typical molecular dynamics and also Monte Carlo. So we've seen this before, but not exactly in this context. This is the energy, and you're going to have the binary potentials between the things, and then ternary potentials and quaternary potentials, and then that could go on forever, right? And then you can have so you can have potential interactions between twos and twos. So it's not just a linear sum, 1, 2, 3, 4, 5, it's also 2 and 4 and 2 and 5, and every other possible combination. So it's not possible to kind of get everything, right? So the way it's broken down, this is all the simulation in lamps, and you'll see in lamps, this is how it's going to go. So this is the energy. So if you take the energy is force times distance, the change in, so if you take the derivative of this, you get the spring constant times the distance, the two cancels. Then you have just spring constants times distance gives a force. And when you integrate that, you get the energy. Integral of force dr gives the potential. So this is what an energy for a harmonic spring is. Some distance squared times the spring constant divided by 2. So that you'll see like over and over and over and over again. You'll see it in the simulation this Friday. That's just the potential that everyone will use. And it means it's a Hookean elastic. It's a linear elasticity. The force is proportional to the distance. In other words, stress, force by area, and strain, distance by distance. has a single constant, and if you plot stress and strain, it's straight line, that's linear. So even though it's squared, it's a linear response, constitutive response. That's a constitutive parameter. All right, so you figure out, like, for all these different things, like what that number is going to be. So you have a ballpark idea what it's going to be to give you the energy, and you can sum up all the binary bonds in the system. So say a polymer, all the spring constants, and it gives you the energy of the polymer. So if you randomly place, say in a molecular dynamics, all the atoms somewhere, so some of them are stretched, some aren't stretched. And then you're going to find out that, oh, the stretched ones want to spring back and the squished ones want to spring the other way. So then you'll get, if you let the thing run, so you take time steps, and then you'll find out that this will reach some equilibrium kind of spacing for the atoms. Right, so that's the first level, the binary level. Then you say, if it's polymer chain, you're going to have like a bond angle. And then you say, oh, well, that's just going to act like a spring too. So, I mean, it's going to be like a pair of scissors that want to be at a certain angle. So if you squeeze the angle or pull the angle, it's going to spring back to that angle, like 109 degrees for carbon-carbon. Right. So you have that, that's like, so theta 0 be 109, then you have, it can change, and you say it's like a spring constant. So I have a spring constant, and I just square that. And it's just a springy, Hookean spring linear response. Constitutive response is linear because force times changing the angles are linear, proportional to each other. And then you take the integral, you get this square by 2 thing. Right. So that also you'll see all over. And then you can say, well, if I have a polymer, then there's also like another level, like it can have a what's it called? Can be shaped like up, over, down, and that can be a crankshaft. Crankshaft is a word. I'll remember the other word too in a while. So a crankshaft motion. So that's going to be a torsion on the molecule, and then you can do more than 4, but usually those are the ones you're going to see. Like that's enough to talk about to make a polymer look like a polymer. And again, if it looks like it, it is it. That's the rule of the game here. So you've definitely simplified things. Basically, the other things are probably not of importance. So you'll see those 3 in the simulation this week, and basically you'll see those no matter what you do, you'll see those things. So you shouldn't be shocked to see the angle squared. It's just a linear response equation. And then Coulomb's law is like the charges squared 1 over the distance to get the potential energy for charges. That's pretty standard. And then you plop in this 612 potential. Anyway, so that's the standard potential for used in organic materials, at least. They have this kind of potential well. So these are things, these last 2 are not necessarily bonded things. They could be bonded in the chain, but they can be things that are some distance. These things are bonded together or in a crystal. So these can be also exactly the same things used in a crystal, Gesundheit. So it's basically, these are kind of bonded together chain units, or they're in a crystal. And then this thing is like things that aren't glued together, right? So in the case of like salt, these would be like the charges in Na and Cl. Right, so you can add up the crystal structure this way, or you can do anything this way, right? And then the 612 is like the standard other things that aren't charged. It's like basically van der Waals is if you have electron clouds around the atoms, and electrons randomly moving from one side to the other. So that temporally one side can be plus, one can be minus, and there's another one near it. There's a plus and minus that can be induced in the other atom, right? So, but the charge interaction goes with 1 over r. So if the 2 charges happen to attract each other, that's more important than if they repel, because if they repel, they move apart, and it's 1 over r. So if you average those out, it's an attractive potential. That's the van der Waals potential that attracts things. Things want to stick together. Right, so it follows basically, this is an empirical law, and it follows like it'll generate a well where they decide to be a certain distance apart. there's a hardcore potential, which is a 12 part, and there's this kind of charge thing with the 1/r thing. So they add up to this well thing, which everyone's seen before. So in ceramics, they use this Buckingham potential, which is the same. They just substitute the 12 part for an exponential. So it's got to be some kind of steep decay, steep potential well, right? So you can use an exponential if you want. Anyway, so there's that business. So let's see. So what's this business? Da, 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 da. All right. So we have these choices, like we aren't dealing with lattice dynamics, right? So just dealing with Monte Carlo and molecular dynamics for polymers. Lattice dynamics is kind of the same thing, adding up the energies, but anyway, so skip that. Skip this. So we're mostly calculating heat capacity for solids. This is from the other class. So Monte Carlo is the thing that's important here. So if you say, I want to get the average, say, energy of the system, right? I mean, Q can be any parameter of density, energy. Those are the two things that you're kind of looking at, I guess. So Q can be energy or density. And then P is the distribution function for the energy of a state of the system. So a state of the system means you have a bunch of spheres. Maybe I do need this thing. I don't know. So you're always dealing with some kind of if it's going to work. So you have a bunch of things. See, I mean, you always kind of say spheres, right? So you have some things. So there's that state and there's this state, right? So there's like a crystal. So Z is like the state. So this is Z equals 1. This is Z equals 2, right? And you could have another state, Z equals 3. So it can have these different states. So you can calculate these energies like K R delta R squared is an energy. And then the whatever, there's no torsional energy, they aren't bonded, but basically you can have the Q1, Q2 over R energy. So you can sum up all those energies in the 612 potential energy, right? So you can sum those things up for the system, then you get the sum of all the Z states energy for the system. Let's say that one's 10, that one's 5, and that one's 50. Right? So you can have all those energies of the state. Then you say, what's the probability of that state of Z? Say Z2, right? Then you got to say it's going to be the Boltzmann probability, like minus minus the sum of the energies that you had divided by KT, then the sum of the states from like 1 to whatever n of all the energies of the system, right? So it gives you the probability of getting that state. This is called the sum of the states. It's usually called capital Z, but he uses Z for the state here for some reason, for this in this slide. But so that's sum of states. It turns out that sum of states, if you take KT times ln of the sum of states, that's the actual free energy of the system. That's a number that's the free energy of the system. So in order to get the free energy for the system, you need to have all the states. But in the molecular dynamic simulation, we have one state. So you can't exactly get this number, so you can't get that number. But you can get the changes between these things. Right. So it's kind of a thermodynamics nuance. But anyway, so that's the picture. So you can see that like knowing thermo and things is pretty good. So if you do that, so you can say, well, I can get the probability of the system, and I can say like, oh, what's the system after that? Like I just need to know the energies of all the interactions and get the system. But if you do that, just the Monte Carlo, if you do that, you'll find out that the energy of the system is an absolutely perfect crystal that's infinite in size, because that's the lowest energy state of everything. The entire universe would be made up of just perfect absolute crystals. with nothing else, right? Because that's the lowest energy you could possibly get. So that process doesn't work if you want to simulate a real system. So to simulate a real system, you have to put in a twist to it. So you have to say, sometimes something bad is going to happen. Like in other words, that's the system where like everything perfect happened. The world's perfect. It's a perfect crystal. It's infinite in size. It's a boring world, and then you have to put in some kind of a twist to it. So you say, yeah, so I'm going to calculate the energy for one of those states. So start with a random state. I'm going to calculate the energy, and then I'm going to move one of the balls around someplace else randomly. Just pop it, right? So you could say that's like thermal motion or something, right? Or whatever. But then I can calculate the energy again, and it might be that the monkey pushed the key and he wrote Shakespeare's play, or it might be that it made it worse. But sometimes, if you want to have the actual world, it has to be worse sometimes. It can't always be perfect. So this is called the Metropolis method, which is Metropolis was a Greek guy that invented it, not the city thing. And then Monte Carlo so this is the Monte Carlo Metropolis method, actually, right? So Metropolis invented it. Monte Carlo means that he's going to allow some kind of random bad thing to happen. So move one atom, if it's lower, yes, that's how it is. If it's higher, then he's going to calculate that Boltzmann difference factor. It's like the difference in the energy between what it was and what it is now by KT, and that gives him a number that's going to be less than 1. And then I'm going to take a random number from 0 to 1. And then every time I do this, I'm going to get a new random number. So that's not a fixed number. And then if this thing happens to be lower than the random number, then I'm going to take it. I'm going to randomly take the bad thing weighted by how far I am, how big of an energy difference I got. So for really big energy difference, it's less likely it's going to beat the random number, right? And if for small energy differences, it's more likely. So it still depends on how big the energy gap is, but it's randomized that you could possibly accept something that's so terrible, right? So in that way you can overcome an energy barrier, right? So there could be like you're in a well, you're stuck there, you can't get out of it, but because you can allow something that could pop over it, and then it can find this very low energy place, and then all the stuff can kind of follow suit and go to that, right? So anyway, so it's a useful thing. It's not new. So this is an example of it on a, see, let me do this. I think I have to do something, let's see. Yeah, I have to say enable editing there. This is what I don't see. Is it? Oh, yeah, okay. Yeah, that kind of thing is invisible to me. It's like being colorblind, except it involves logic. So anyway, so you can go here. All right, so you can write a program to do this yourself, This is a 2D model of doing that, right? So you can also make it 3D, which would be better. But basically, this is just looking at so icing was a magnet thing, right? So let me go back over here to say what icing is. So they call this an icing model, but what you're looking at is like phase separation. But an icing model, you have magnetic domains, and they can be like they have a magnetic moment. And if you put them in a field, like a magnetic field, well, they can align with the magnetic field, or they have two states. So they can be black or white, right? So basically they have two kind of normal states. So this is icing model. And it's kind of intimately tied to the Metropolis, whatever, Monte Carlo method. These things are linked together more or less, but so you have all these lattice sites, and each one has an arrow in it, and then you can say like up and down or black and white. So if you dot those, you get an energy. If it's black, that's a low energy. So that's like -1. If it's white, black, it's like +1. And if it's white, it's -1. So you're going to sum up the energies between all the binary pairs in it. That's going to give you a system energy. And then if you flip one of them, then you get the new system. And you can see this is the basis of that idea of flipping something, right? So anyway, so that's what you're kind of looking at as an icing model. It turns out exactly you can get like spinodal decomposition and binodal phase separation, everything just from that simple model. So you can tune the temperature. So he's got the magnetic field, which could be the chi parameter. In other words, the field could be the chi parameter. It could be an electric field. I guess those are the three things, like an enthalpy, a mean field enthalpy, like a Hildebrand enthalpy for the mixing, demixing. And then it can be a magnetic field, an electric field, probably something else that you could dream up. But basically there's a field that's guiding the thing. And the temperature overcomes the field. So if you raise the temperature, it'll go random. Looks like noise on a TV set. And then you cool it down, then it's going to phase separate. Theoretically, it would go to total phase separation. Maybe if you bring the field down, right? So this thing happens pretty fast, even though it's just an app. Sweep, skip, I don't know. That's like just what it's displaying. And you can go to different size things. So you can see it looks all like spinal decomposition. You can basically do spinal decomposition with this, or you can get bulk phase separation. So it's nifty. I mean, it works. And you can do basically more complicated things than the icing model with this. So it's the example of it is the icing model because that's where it was first used. But anyway, you can find it'll have a critical temperature where you can see phase separation. The critical temperature depends on the size of the system. That's what you could play around with this to find. So the phase separation will happen faster if you have a small system. In other words, when it'll go all black or all white if you have a smaller system earlier than if you have this huge system. There's a couple things you could do with this if you want to play around with it, but anyway, so it's just a way to, it's not real, but it's just like a way to look at systems, and it agrees pretty well with reality. So they say it's true. Typical computer simulation thing, right? So there isn't any concrete link between this idea and physics. It's just like it works pretty well. So you can see where it's going with machine learning and artificial intelligence. If it works, it's true. That's the basic premise of all of it, even the simulation things, right? So anyway, so that thing, if you want, you can play around with that. There's a bunch of these on the internet, by the way. It's not just that one, but that's the Monte Carlo. So the molecular dynamics doesn't have that. It doesn't have this kind of jump over the energy barrier thing. It doesn't even approach the thing in terms of that at all, right? So it's basically like, this is just your pool table with the balls. You shoot the ball in, it's got a velocity, it transfers momentum to the other balls, then the balls go over and one of them ends up in the hole, right? So that's molecular dynamics. And in order to do that, you do steps. So you're going to do time steps as delta t. So you're going to have like the velocity, and then there's an acceleration, and then a position of the atoms. So you have for every ball in the system, and they're not on a lattice, so they're just floating around. Each one of them has a velocity and a direction. So magnitude and a direction, and the same thing for acceleration, and the same thing for its position, x, y, z. And then since you know the velocity, it's a time-dependent thing. If you have a change in, so it's going to move positions, right? And then it's just kind of, you set up the rules, like you have the spring constant between the atoms, you have a torsional thing, you have a torsional and an angular flexing. So you have all those components, and the 612 potential and the charge potential thing. You sum those up, and then you can get something that looks a lot like kinetic theory gases. Like things are bouncing around. So the first part of the homework thing is like do kinetic theory of gases with balls and use those potentials, and you'll see it works great. Like you can get a diffusion coefficient, it follows Brownian motion, it's perfect. So yeah.
I think time step.
Yeah.
And choose a good one for them.
Well, it's got to do with the diffusion coefficient for the particles, which has to do with the potentials that you put into it. So time step, so everything's linked together. In fact, the time is just going to be a unit time. And it's based on the parameters you put in for the constants. And the constants, the spring constant, all those things are unitless based on KT. So it's going to be a fraction of KT is going to be all the energies that you have in it. So basically everything is unitless. And then they say it's picoseconds in the end, because the spring constants of atoms, if you add those things all up, the time you get is a picosecond, which adds up to nanoseconds if you do it long enough. If you say, so you can see like it's coarse, if it's coarse grained, then the ball could be anything. And then those interaction energies diminish as you go to larger sizes. So that, and eventually you need gravity in it too, right? Because at some point gravity matters. So if things have no mass, gravity doesn't matter. So if they're an atom, it doesn't matter. But as you get larger to colloidal sizes, things settle, like there's a settling that can happen. And in the same thing, so you can do anything you can do in the real world, you can do in lamps. Like you can make the thing flow. You can take a solid chunk and stretch it inside lamps. So you can do an instron test, but you're dealing with like 100 atoms. So it's an instron test on 100 atoms. You can get a modulus, but it's a modulus of 100 atoms. Or if you define that those things are bricks, then it's a modulus of a building, right? Or a wall. So it depends on everything depends on what you say those constants are, just in your mind, what it is that you're looking at. But you need to have the potential, like if it's a wall, you definitely need gravity. If it's atoms, you don't. So, and there's not going to be any ionic potential for bricks, like that's insignificant. No matter how much you charge a brick, it's not going to repel another brick. I mean, there's some point where it would, but basically it has to be, I don't know, a huge amount of voltage. Right. So basically, what you throw in defines a time scale. It's not a fixed number. But if you're dealing with atoms, it's picoseconds. And that's defined by the potentials that come out of like Leonard-Jones potential and everything you put in that come from what other people did because it worked. And it worked means it came out with something that looked like whatever you thought it should look like. So it's not science. It's never science. It's just like, it looks right. Doesn't mean you can't discover things that you believe are true. I mean, so you can use it to generate thoughts that you believe are true, but they're not true. So until you prove it with an actual system, it's not exactly true. But you can use that to build a whole universe if you want. I mean, computer video games are based on that. So you can see, and it can look pretty real. Maybe it is real, maybe it isn't. It could be real. So, see, I mean, at some point, a lot of things are based on just you think it looks right. I mean, the original theory for like orbiting shells for electrons, where they have rings and they fit into the rings of different energy levels. So that was believed to be true, and it was kind of true, like you could predict things with it. So in a sense, it's like that, I mean, you could say, well, that was a little bit more based on fact, though. This isn't based on fact, really. It's based on you look at it and it looks right. That's different than actually measuring something and having an error bar. And you can say it's this much correct and that much not correct. So anyway, you have to be a little careful, but basically it's fun to do, I think. For some people, this is like totally enjoyable to do this kind of thing. And then have it come out with something that looks real. There's many papers written on this. The nice thing about it for this class is that in order to do this, you need to use physics. So you need to have like Polymer Physics as the basis of it. And experimental or chemistry, it's a side thing. You don't necessarily, in order to make a new rubber, you don't necessarily need to understand rubber elasticity. They can just cook it and it comes out and then you make a sneaker with it. That's great. So you don't necessarily need to, but with this, you can't do a single thing unless you start with some kind of equation that's based on physics. So the first thing you do, you need the spring constant. So you need Hooke's law. You need to kind of understand that in some detail, right? So anyway, it's built like that. So anyway, so you can see like this thing is going to give this mean squared displacement, going to give the diffusion coefficient, and that's going to give the time scale. Right, so you have Brownian motion, it's going to give you the time scale straight up, because all the motion of these particles, which are based on the spring constants you put in, are going to generate time. So the time step is based on what you put in. But anyway, so you just So you're gonna have something, so you're gonna do that motion. So you start out, the thing is not at equilibrium. So you just say, oh, say it's in a perfect grid, and I'm gonna start there. Or just say I'm gonna randomly place the atoms. Random means some of the atoms will be on top of each other, right? And then, oh, I can correct those. So you can have routines that set up the initial state. And your result might really depend on the initial state. Like this isn't clear that whether the initial state is meaningless or not, because you don't have a way to overcome energy barriers. So if you happen to put it in a local minimum where it can't get to the other thing, then that's a big problem, right? So there's many ways to look at this. And then they're going to let it cook along, and then you're going to go like, well, after so long, I'm going to get to the I'm going to measure the temperature of the system. So 1/2 mv squared is kT. So all my v's, I can sum those up and I can get a temperature for the system. So I can plot temperature versus my time, which is made up of these little delta t steps. And say like, oh, the initial temperature is here, and then it like goes up, and then finally it kind of reaches something. But generally it's going like this, and it's a little hard to tell, like, have you really reached the plateau or not? Like, how much time do you need to wait till you say, yes, that's equilibrium. I've reached the state, and at equilibrium, that's my picture of what I'm going to get. Or you could do that same thing with density, like the density of the system or the free energy of the system. The quote unquote free energy. Again, you can't get the total free energy because you don't know the partition function, the sum of states, the exponential minus potential of whatever over kT, the sum of all of them, because you don't have all the states. So you can't get the actual energy. We can get something like the energy of this state, kind of this, whatever you're looking at. But anyway, so anyway, that's how the dynamics, you'll see that with the lamps thing. Anyway, there's some other things. Density functional, and then there's lamps, right? So lamps is just all downloadable. So we'll do this on Friday. Like you can go to their webpage and it's got everything in it. That's pretty weird. Yeah, no, that's all right. Research area. That's oh, thanks. See, that's totally invisible to me. Like there's something about my brain lost the ability to pick something out that's right in front of you, like a stop sign. Just zip right through it. It's like no problem. One day I will be dead. They need an answer why it's a dysfunctional observational skill. Anyway, so you can go here. Better is like, say you want to do like just do lamps, uh liquid dynamics, liquid crystal assembly. And then you'll find like people have done it already. And then you can find their GitHub code for liquid crystal molecular dynamics assembly. You can just copy it. And then you can tweak it to get it to how you want it to do. I don't know if these are videos or. So basically lamps is so popular that you can find anything you can think of is already there. I think you can probably use chat to do it too. Probably better and faster, right? So I'm not sure if I have to sign in to use this or what. Maybe I can't use it here. But if you put it into chat, it'll write. So it's a scripting language. It's going to use Python and just a bunch of scripts, a bunch of commands. You'll see. It's just like put this command and then it does it. So it's, I think it used PyTorch or something. So it kind of goes through. Just it's a interpreted language. Just type in the line and it does the thing, you know. And you can type in a bunch of lines and that window, you can say operate that window, and then it just does it. So the operation comes out right below it. So you got to get a little used to doing that, but it's pretty simple. It's like how BASIC was originally. You write the line, it does it. You know? So then they made BASIC into like a compiled language instead of just 1 + 1 = what. And it gives the answer, you know. So it was originally just a calculator. But so that's what this is. Interpreted language is kind of just a calculator, but they can use different script codes that have been programmed into it to do things. Right. So anyway, so this is like that. I don't think I can ask a question here as far unless it's right in front of me and I don't see it. But I think I have to somehow. I can do it on my computer when I'm not here, but this will be really useful to write code in LAMP. So you can just say, what's a good script and lamps to do liquid crystal self-assembly or anything you want. Make a membrane that transports hydrogen. Model that in lamps, and ChatGPT will give you the code. Like so, or you can Google it and you'll find that people have done it. That's what ChatGPT is doing, is just Googling and finding it and assembling it for you. Anyway, so it's pretty powerful. There's a slight learning curve, so you'll have that learning curve done by next Monday, I think, or whenever it's due. Right. So I think the learning curve isn't that significant. Like it's a little bit of like it's a pain in the neck, then you figure it out and it's like this is pretty easy. Right. So so many people have used it. It can't be that hard to use, you know. So I think you can do it. Then if you say like, oh, this is going to take a week on my computer, right? And that seems to be like too long because I also want to play video games on the same computer, right? So you can get this. So there's this collab that's free. It's like a Google, or they'll give you a supercomputer for more than time than you ever will want to use. So you write your script on your PC, get it to run so there's no bugs in it, and then you can just port it over to this collab thing, and it'll run what would have taken a month for you in like 2 seconds and spit out the answer, right? And also for anyone at UC, you can use the Ohio supercomputer, Ohio State, and you can get like $4,000 worth of the supercomputer time for free a year. After that, you have to pay. So they addict you. It's like the first one's free, and then like, yeah, no, you got to pay. But the pay, even when you pay, $4,000 is enough to do a PhD dissertation. So if you're going to do 2, you got to pay another 4. The first one you can get, and if you're willing to wait the extra year, you get the next one free too. So it's basically it's between those 2, and there's probably some others where you can get onto a supercomputer if you need it, which you probably don't. The other thing you can do, so what they do is they're going to use like graphical processing units because they run faster for dedicated tasks, like doing some math calculations. So basically, like Nichols has a computer set up with like 30 GPUs in it. So his is like a micro supercomputer. Like instead of doing it in 2 seconds, it'll take an hour. So basically anything, because he's doing the membrane calculations and stuff. So basically you can use his computer for free, or you can buy him a beer or something. But so it's possible to, once you figure out, so the hard part of this is this first step of just like downloading the stuff, figuring out how to put it in your computer, a couple of little bugs about making it run. Then you find out that, yeah, you can do a polymer that sticks to itself and self-assembles. Right. And pretty much you can tweak that and do whatever you want with that model. Then if you Google whatever it is you want to do, you can find something else similar to that where it's just the code is there and you can port it in and just mess around with it and get it to do what you want. And if not, there's actually like thousands of people that will collaborate with you to do this. It's like there's so many people, there's almost like a club of people, and they're really excited about helping you. Like if you just talk to them and say, they'll come and they'll like help you do it. If not at Sandia, but then all over the world, right? So basically it's a club, it's almost like a video game. So alternative to that is this Homemade Blue, which also has the same kind of setup. It supposedly runs faster on graphical processing units. So then there's this DPD. So you forget about, we're out of time, but DPD, you forget about all your things about 612 potential and spring constants. You just say, I'm just going to have linear relationships between everything, and they're bulk scale, so 612 doesn't matter anymore. So these are liquid crystal self-assembly from a random phase to a smectic phase, where they like form lines eventually using DPD, which is, and it looks like what happens, So they said it worked. So it's like you don't need to use even physical equations. You just say everything in the world is linear. That makes the calculations like thousands of times faster. This would be like macro. It's like the display in your watch, or I don't know if they use that in watches anymore. Basically, like an LCD display, like how it makes it see or not see. Anyway, so that's about it, I guess. Anyway, there's more in these slides if you want to look. This kind of goes through DPD stuff. That's it. So that's good. I got through that. the ML AI, he talked about in the symposium, actually. So there's, in his introduction of it is probably better than mine. So basically, if you want to see the ML AI, I didn't have time for, go to this. If you didn't go to the symposium, it's like right here somewhere. Then you have it, nanoplastic pollution, and then those are those papers, and then the materials modeling simulations thing. Oh, that's me. Why is that there?
It's in the class report.
Oh, yeah, it's in class record. See, that's right in front of me. I don't see it. So it's like soft matter symposium. So it starts with, this is Sanat's thing. He's talking about, actually, he's talking about membranes, and he's using machine learning for membranes, so he goes through in detail the pitfalls of machine learning, AI and stuff. Like he's getting data from the literature at first, and he finds out in the end that not one of those data sets is of any use. Like they're all wrong, So he has to do his own, and he finds out he can get like perfect correlation. It's really interesting. The guy gives a good talk, So basically that's probably worth looking at if you're interested in that. All right, so that's it. So next week I'll do membranes, which is this subject too, but right. So kill this.